We're going to start this week off by talking about linear transformations. So a transformation is just another word for a function. This function is going to take and transform things from one space into another space. If you've taken Calculus 3 before, this occurs when you go ahead and you try to change variables. So for example, you can go from rectangular coordinates to polar coordinates through a transformation. That's kind of what this figure is talking about, how we have kind of these rectangular coordinates, x, y, and it makes them rectangular by using kind of r and theta to kind of change what our coordinates look like. Another example of a transformation is when we project from one space onto a lower dimensional space. So for example, we could take kind of this line of points in R2, or this curve, and just go ahead and denote it by its y-axis component. So we have just kind of the shaded area. Lab 2, Radiography Lab 2, for us it's Lab 4. We found that if we apply a radiographic transformation to a linear combination of vectors, we got a linear combination of their radiographs. This property is kind of cool and useful because we might wonder what an object is kind of made out of. So if we know what part is being radiographed, then we can kind of take away some things to figure out the parts of the radiograph we don't know. So kind of, for example, suppose we took an object and we expected to see something like this on the left, but in truth we actually get something like this on the right. So maybe this is what we see, but maybe this is the thing we're getting. Then we'd expect that the radiograph comes from this object, x expected, but maybe it comes from something else. And so what we can do then is we can remove the things that we expect to see to figure out kind of what these other things that are happening are. So in order for us to get to this part and kind of see where things are coming from, we need to understand linear transformations. So here's kind of some definitions. Let V and W be vector spaces, and let T be a function that maps vectors from V into W. We say that the transformation from V to W is a linear transformation if both of the following properties are satisfied. For any arbitrary vectors U1 and V1, the transformation of U1 plus U2 is going to be the same as T of U1 plus T of U2. And if we have a scalar in a vector, and the scalar is alpha, vector is U, then T of alpha U is the same as alpha times T of U. Now what's important about this is that we have to verify both of these things. Sometimes it might seem obvious, other times we will find that it doesn't work out, and so we want to make sure we can identify what things actually are linear transformations. We could combine these steps into one if we just took T of alpha U1 plus beta U2 and verified that it was the same as alpha times T of U1 plus beta times T of U2. So we also can call T a linear function or a homomorphism, just in case you recognize this from other classes. To check that T is a linear transformation, we're going to take two arbitrary elements in V and an arbitrary scalar and verify that these two properties happen that we had talked about. And the reason that we want to go ahead and make sure we can do this, or kind of maybe a visual representation of this, is say we start off with two vectors. What we're saying is that we can go ahead and add the vectors first and then transform them, or we could transform the vectors first with our function and then add them, and we should get the same thing. Similarly, we could go ahead and multiply our vector by some scalar and then transform it, and we should get the same thing as if we transform it and then multiply by that scalar. So let's talk about considering a map from R3 to W, where here W is just going to end up being the real numbers, where if we transform some vector ABC, we'll get A plus B plus C. Then T of 1, 2, 3 would be 1 plus 2 plus 3, which is 6. We want to go ahead and determine whether or not T is a linear transformation. So we need to check our two properties. We need to verify that T of U plus T of V equals T of U plus V for two different vectors U and V. So what we're going to do is we'll transform some U1, U2, U3 and some V1, V2, V3. So these are arbitrary vectors in the domain. And what happens if we transform both of those is we'll get U1 plus U2 plus U3 plus V1 plus V2 plus V3. Now note that this is the same as T of U1 plus V1, U2 plus V2, U3 plus V3, because this would just be taking U1 plus V1 plus U2 plus V2 plus U3 plus V3. So since these two are the same, this first property checks out. So we're good to go there. A little bit of a check mark. And then the other property we need to verify is that T of alpha times U equals alpha times T of U. So to verify this, we'll see that if I take T of alpha times, say, U1, U2, U3, that will be T of alpha U1, alpha U2, alpha U3, which will be alpha U1 plus alpha U2 plus alpha U3. Now let's compare that to T of U1, U2, U3 times alpha. This is just alpha times U1 plus U2 plus U3. But notice that these two, again, are the same. So if we just distribute this alpha through, we get this. And so since both properties work, we can conclude that T is a linear transformation. All right, great. So we've got a linear transformation. So I want to kind of just look through a few more examples of things that are linear transformations and kind of figure out whether or not they end up being linear transformations. So on the next page of the notes, we've got two examples, 4.4 and 4.5. I encourage you to pause the video and try both of these on your own, and then kind of unpause it and see if you can figure out what the answer is, or understand what the answer is. All right, came back? Great. So we want to know whether or not this map is a linear transformation. And so we want to check. If I take f of alpha x, is that going to be the same as alpha times f of x? So we need both properties to work. I'm just going to pick one of them. And so here, if we take alpha f of x, that's f of x is going to be 2 alpha x plus 1. So we just take the alpha x and we substitute in for x. Whereas on the other side, we'll get alpha times 2x plus 1, which, again, we're trying to verify that these two things are equal. So we'll have 2 alpha x plus 1 is trying to be equal to 2 alpha x plus alpha. Well, unless alpha is 1, which we're not guaranteed, these two will not be the same. So not equal in general. So with that being said, this will not be a linear transformation because it doesn't satisfy one of our properties. So let's then keep in mind, or try to use this to figure out if there are any restrictions if I have f of x equals mx plus b in order to make it a linear transformation. Do I have any restrictions on m or b? So this is kind of weird, right? We think of this usually as the equation for a line, but it's not a linear transformation. So what counts then as a linear transformation? Well, let's kind of double check our properties. If we check if f of x plus y equals f of x plus f of y, that first property, here what we would see is that if we have just some sort of generic mx plus b, f of x plus y is equal to m times x plus y plus b. On the other side, we have mx plus b plus my plus b. And so we have m times quantity x plus y plus b equals m times quantity x plus y. We can kind of group things together and factor them out here, plus 2b. So this is only true if b equals 0. So here, anything that says that b can be anything, this one's not going to work out, this one's not going to work out. Okay, so, I mean, yes, we like cats. That is also an answer that's true, or at least I like cats. You sometimes don't even hear the cats running around in the videos in the background. But we want to check our other property as well. If f of alpha x equals alpha f of x. And so here we would have m alpha x plus b equals alpha times mx plus b. And so kind of continuing along here, we have m alpha x plus b equals m alpha x plus alpha b. And again, this equality is only true if b is 0. So when all is said and done, we didn't have any restrictions on m. So m can be anything. So in the end, the answer ends up being C. All right, so something that we can use as a bit of a helpful property. The proof is here if you want to take a look at it. Let's have a transformation go from V to W. If it's a linear transformation, then T of 0 is going to have to equal 0. So kind of a quick check you can do to determine whether or not something is a linear transformation is see if T of 0 does indeed end up giving us 0. If it's not, it cannot be linear. But if it is 0, then we still have to do all of our things to check. But if it's not 0, it's not going to work out. So let's say we had a function defined from R3 to R2 by taking some vector that was the input and multiplying it by a matrix and adding x. This vector x is 1, 0 to the end of it. Well, what we want to do is we want to double check if f of 0, which in this case would be f of 0, 0, 0 as a vector, gives us 0. And so we'll have 1, 2, 1, 1, 2, 1 times 0, 0, 0 plus 1, 0. So when we do this multiplication, our first entry should be 0 plus 0 plus 0, which is 0. Our next entry should be 0 plus 0 plus 0, which is 0. And so we get 0, 0 plus 1, 0, which is going to equal 1, 0. So because of our theorem, we can verify that this is not a linear transformation. So not f is not off the screen now. Linear transformation. I might denote lin trans for linear transformation since f of 0 is not equal to 0. So it's a theorem we have that we can kind of use for ourselves. All right, let's check maybe another couple examples. So let's say that we have a transformation going from P2 to P1 where we take some ax squared plus bx plus c and we end up getting 2ax plus b. So quickly we can check if I look at t of 0. In this case, t of 0 is t of 0x squared plus 0x plus 0. So remember that when we're looking at transformations involving some sort of some polynomial, and we're looking really at the a, the b, and the c, right? The x squared, the x, the constant part, they're placeholders to help us verify and identify what numbers we're taking when we're doing this transformation. And so here we're saying that we have 0x squared plus 0x plus 0. A, b, and c are all 0. And so that means we get 2 times 0x plus 0, which is 0. Okay, so we didn't break it, which means we have to check our properties. So we need some sort of vectors so we can check if t of u plus v equals t of u plus t of v. So with that being said, we need kind of polynomial vectors in P2, u, and v. So we're going to say that u is equal to a1x squared plus b1x plus c1, and v is equal to a2x squared plus b2x plus c2. It's just to kind of help us keep track of where things are coming from. So t of u plus v is going to be t of a1x squared plus a2x squared plus b1x plus b2x plus c1 plus c2. And so here, note that this is the same as t of a1 plus a2x squared plus b1 plus b2x plus c1 plus c2. And so kind of the reason we want to make sure we group these is so we understand what our quote-unquote A, B, and C are in this case. And so doing this transformation, we end up getting a result of 2 times a1 plus a2x plus b1 plus b2. We also want to go ahead and check t of u plus t of v. So that's going to be t of a1x squared plus b1x plus c1 plus t of a2x squared plus b2x plus c2. And so we end up getting 2a1x plus b1 plus 2a2x plus b2. But notice that what we got by taking t of u plus v is the same as t of u plus t of v. So these are the same. So that's the first property verified. We still need to verify our other property, which is t of alpha u equals alpha times t of u. We've already determined what t of u is, though, so that can help us a little bit. So let's look at t of alpha u. That's the same as t of alpha a1x squared plus alpha b1x plus alpha c1. And so that'll become 2 alpha a1x plus alpha b1 And note that alpha times t of u would be alpha times 2a1x, that's an a, plus b1. So when we look at comparing these two, again, what we get is the same for both of these. So because both of these work, T is a linear transformation. Okay, awesome. So let's take a look at a function t of v going from, or t of v equals av, where a is a matrix and v is some vector in R2. We want to figure out what this is doing. So if we take -1, 0, 0, 1 times x, y, we should get -x, y. And so if I've got some xy point here, then -x, -y, or sorry, -xy will be over here. So this is something that reflects over the y-axis. So here's our y-axis. Here's our y-axis. We were on one side. When we switch the x to be negative, we end up on the other side. So here we've got something that's a transformation. We can verify if it's a linear transformation. And we can go ahead and when we define it with this matrix, it will go ahead and reflect things for us. Alright, so why are we talking and caring so much about these linear transformations? So functions are relatively easy for us to understand, but it would be nice to encode them into a matrix in some way, shape, or form so that way computers could understand and use the functions as well. Matrices tend to be a good way to store information in a computer. They're also at times easier to work with, and so if we can code a linear transformation based on the formula, sometimes it's hard, but if we can use and turn them into a matrix, then it'll be easy for us to go ahead and use linear transformations with computers. So let's maybe talk about an example that suggests that this would be a good idea. Let's say we had a transformation defined from R2 to R3 by taking, and if I wanted to transform x, it would be equal to m times x, where m is just a 3 by 2 matrix. We can show that t is actually a linear transformation using the properties. So if I want t of alpha x plus beta y, so that one-step check, that's the same thing as the matrix times alpha x plus beta y. And because we can distribute the matrix on the left-hand side, we get m times alpha x plus m times beta y. Because alpha and beta are scalars, we can pull them out to the front, and then we end up getting alpha t of x, because mx is just t of x, and beta times t of y, because my is just ty. And so we very easily are able to show that matrix multiplication can help us define a linear transformation. So what if we could define all of our linear transformations this way? That'd be really cool. So the issue, though, is that we can't just multiply some vector in, say, P2 by a matrix. So remember, P2 is going to be the set of all ax squared plus bx plus c, such that a, b, and c are in the real numbers. So here, if we just took something in this and multiplied it by a matrix, that might not come out the way we want it to. And so our keys to the system, our ability to go ahead and just use matrices, is going to be tied into our ability to use coordinate vectors. So later one of the later videos this week is coordinate vectors, and then next week we'll use the idea of linear transformations and of coordinate vectors in order to create a matrix form of linear transformation. So after we have a little bit of an ice sheet in the next video, we will see how to create coordinate vectors.